This is SpaceTime, Series 22, Episode 93. Coming up on SpaceTime. Forget what you've heard. Size really does matter when it comes to galactic rotation. The most massive star ever known to be destroyed in a supernova explosion. And the mystery particles detected around the NearEarth asteroid Bennu. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
It turns out the direction in which a galaxy rotates can depend on its mass. The new findings, reported in the monthly notices of the Royal Astronomical Society and on the pre-press physics website archive.org, will help scientists better understand how galactic rotation builds up across cosmic time. Virtually all galaxies rotate, and this rotation is fundamental to how galaxies form. For example, most galaxies are flat rotating disks, our own galaxy, the Milky Way, being a prime example. The observations are based on an analysis of 1,418 galaxies, astronomers finding that small ones are far more likely to spin on a different axis compared to larger ones. The rotation was measured in relation to each galaxy's nearest cosmic filament. Okay, so what are cosmic filaments? Well, the large-scale cosmic structure of the universe looks a little bit like a web or honeycomb. It consists of strands of filaments composed of huge amounts of matter, including gas, stars, galaxies, galaxy clusters, and galaxy superclusters, as well as dark matter. These filaments surround vast, empty voids. The filaments are like strands of galaxies. They can be 500 million light-years long, but just 20 million light-years across, dividing the universe into vast gravitationally linked lattices interspersed with these enormous dark matter voids. So you can think of the filaments as sort of like gravitational highways of galactic migration, with many galaxies encountering each other and merging along the way. It's the filaments which are why the universe looks like a honeycomb or cosmic web. Using data gathered by an instrument called the Sydney AAO Multi-Object Integral Field Spectrograph, or SAMI, which is attached to the Anglo-Australian Telescope at the Siding Spring Observatory in western New South Wales, scientists with the Asteroid 3D collaboration studied each of the 1,418 target galaxies and measuring each one's spin in relation to the nearest filament. Curiously, they found that smaller galaxies all tended to rotate in direct alignment with the filaments, while larger ones all seemed to spin perpendicular to the filaments. And the spin changes from alignment to perpendicular rotation as galaxies, drawn by gravity towards the filament, collide and merge, thus gaining mass. And as for our own galaxy, the Milky Way, well, its spin is also well aligned to its nearest cosmic filament. But the thing is, the Milky Way belongs to a class of intermediate-sized galaxies that overall show no clear tendency towards parallel or perpendicular spins. One of the study's authors, Asteroid 3D principal investigator Professor Scott Kroom from the University of Sydney, says the results offer insights into the very deep structure of the universe.
So this is research that we've been working on for a number of years now, making measurements of thousands of galaxies where we have been measuring the direction they spin and how fast they spin, which has been enabled by a new technology that we've installed at the Anglo-Australian Telescope in Coonabarra in the middle of New South Wales. And so what we've been able to do with this instrument is not only look at, sort of take an average snapshot of what a galaxy looks like, but actually look in detail at each galaxy and look at its motion of the gas and the stars in the galaxy. And that allows you to see which direction galaxies are spinning. And almost all galaxies spin. There's a small fraction that don't, but almost all galaxies spin. Largely because as gas and matter collapses, there's always some residual spin that is conserved as the matter collapses. This is sort of the physical concept of conservation of angular momentum, the fact that things keep spinning as they collapse.
That's why the Earth spins and why the planets orbit around the Sun.
Exactly. And so that's why most galaxies, when you look at them, look like they're disks, flattened disks, because everything has sort of these random motions as they collapse, and the gravity is most able to collapse things in the direction that has the least spin. And so you end up compressing things along the axis of least spin to make a disk that's rotating. And so it turns out that, of course, unsurprisingly, the spin of a galaxy then is fundamental to its structure and how galaxies evolve. And this instrument called SAMI has enabled us to measure this for thousands of galaxies for the first time. And because we've looked at thousands of galaxies, we can start now to look at how the spin is connected to the broader environment of a galaxy. And so we know galaxies can live in a range of different environments. Some galaxies are out on their own with not much around them, and other galaxies are sitting in the middle of very dense clusters of galaxies with thousands of galaxies surrounding them. And in fact, there's everything in between as well. There's a whole hierarchy of different environments. And what we see in particular when you look on the largest scales is what we often call the cosmic web. So that if you look at the distribution of galaxies on the largest scales, you see that you have this structure of this filamentary structure that connects the sort of the densest parts of the universe, the dense clusters of galaxies. And so with this work, what we're trying to do is trying to understand some of the physical processes that are building the spin and why galaxies spin a certain way. And the data allowed us to connect the spin to the sort of the local structure that we see nearby a galaxy. So in this particular case, we were saying identifying filaments of galaxies. So these are sort of linear features in the galaxy distribution that could be hundreds of millions of light years along with many hundreds of galaxies in them, but they tend to line up in linear structures. Linear structures have random orientations. They're all over the place when you look at a pattern of them, but you have these clear structures that, again, it's with where the matter has collapsed into sort of sheets or filaments. And what the galaxies are doing is flowing into those filaments and then flowing along those filaments. And so because we have a larger amount of data than anybody's had before, what we were able to do was ask the question, well, how do the spins relate to this large-scale structure, these filaments? And what we found was, at least statistically, when you look at small galaxies, they have spins that are aligned with the filaments. That is, as they fall in to the galaxy filaments, the small galaxies are falling in, but they're not perfectly aligned with the filament. They're coming in at an angle, but are also creating matter that's also falling in the same direction. And so they're being spun up in an axis that means that sort of the spin axis is along the filament. And so we saw this signal in the data, but more than that, what we were able to look at is a range of different galaxy masses. And when we looked at the highest mass galaxies, we actually found the opposite signal. And so in this case, we saw high mass galaxies have a spin that on average is 90 degrees offset, or at least it's in that direction. There's a whole range of different angles, but it's more anti-aligned with the filament. What we think is happening is that what sort of numerical simulations seem to show is that when you get the very high mass galaxies, the way they build up most of their mass is not through accreting gas in like small gradual flow of gas, but through merging with other massive galaxies. And when you do that, most of that merging is happening for galaxies that are flowing along the filament. So the galaxies flow into the filaments first, and then they're flowing along the filaments towards the regions of the very high density, so the clusters, the connection points between filaments. And as they flow along the filaments, they're interacting with other galaxies also flowing along the filaments. But again, because it's very rare for them to have a sort of a direct head-on collision, they're always slightly misaligned, you get a spin-up process due to the mergers of galaxies and interactions of galaxies flowing along the filaments, which then leads to an average spin axis which is more aligned away from the filament. It's an evolutionary phase of flowing from the low mass galaxies that are mostly growing through gradual accretion of gas to the high mass galaxies where you're building those up via sort of more extreme interactions and mergers of galaxies.
Does that mean there are lots of low-mass galaxies away from filaments, but more likely to be high-mass galaxies near filaments simply because there's more galactic cannibalism going on there?
So that is true. There certainly is a greater number of high-mass galaxies in the densest regions. And that's for a number of different reasons. One is, you're right, those high-density regions, there's a more chance of growth via this sort of merging cannibalism kind of approach. But also the high-density regions were the first regions to collapse under gravity in the early universe. And so also you've had more time to grow galaxies there. So if you imagine you need to reach a certain threshold in density before you can start having the matter collapsing to form a galaxy, those regions that are very high density now, they would have been the first places where galaxies formed in the early universe. So they've also had more time to form and to grow.
What about somewhere like the Milky Way? There's been a lot of debate about where we actually are in relation to both the nearest filaments and also to the local void. There have been some reports recently that we may even be in a local void, or at least, right on the border of one.
So that's an interesting question, actually. So the Milky Way, at least from our analysis, is an intermediate mass galaxy that would not have any particular preference for the direction it was going to spin due to its sort of local structure. And we do have a bunch of different structures around us. We have obviously the local group, which is just a few 100 million light years across, going from us to M31, the Andromeda galaxy. That's a sort of similar type of galaxy to Milky Way, a little bit more massive, but similar approximately in structure. And then a whole bunch of other smaller, lower mass galaxies around us as well. If you go to a larger scales, there's a Virgo cluster, which is not too far away, but then there is some evidence that there certainly are sort of voids, large-scale voids near us. And these voids can be very large, they can be, hundreds of millions of light years across.
That could affect how we view the entire universe, in fact, especially things like dark energy and dark matter.
Yeah, so there's been some interesting discussions about whether the current local the idea of having a local void is that the void is big enough and deep enough that it can help us understand some of the current discrepancies between different measurements of cosmological parameters like the Hubble constant and those sort of things. And I think it's possible that there's some contribution from that, but I think the jury's out as to whether that's actually the case right now. It's an interesting question, though.
What's all this telling you about the large-scale structure of the universe and the effect that gravity has on that? Because gravity is what this is all about.
Yeah, so that's right. I mean, in the end, gravity is the thing that drives galaxy formation fundamentally. There are other physical processes, but gravity is, of course, the main one. What we're seeing and what's interesting is that these effects are on larger scales than we originally thought. So this is the first time where we've really seen evidence that the gravitational effect and the local large-scale structure has an effect on the spin of galaxies outside of their local overdensity. So what we think the way galaxies form is that the normal matter, what we call the baryons, the gas, the sort of atoms that make up you and me and the stars, they collapse down into a galaxy, but within what we think is a dark matter halo that we don't directly see, but we can see indirectly through its effect on the spin of things and through things like techniques like gravitational lensing and a number of other approaches. Now, what we expected is that within those dark matter halos, that the way matter collapses affects the spin, and that's a natural thing to happen. But what this is now telling us is that the larger scale structure actually drives spin as well. So it's not just sort of the local effect of exactly how the gas collapses within the dark matter halo, but a much larger scale effect.
It points to the reach of gravity, but that then also raises questions about the debate between gravity and dark energy. I mean, we know that dark energy is causing the overall expansion of the universe. There's plenty of evidence of that, but clearly gravity still has an enormously powerful reach, even over large distances.
No, well, that's right. I mean, gravity, it's never, the force of gravity never drops to zero. I mean, it goes as a classical Newtonian inverse square law. And so it always has some importance. It just depends on the scale and exactly what situation as to how important it is. And the interesting thing is that, of course, as you go through, if you run the clock forward even more, eventually, the galaxies that we're seeing flying onto filaments, by and large, will collapse onto those filaments and will grow into those filaments and slow down those filaments, but very slowly. I mean, they're still only moving at least cosmologically small velocities, which are a few hundred kilometers a second, right, to maybe 1,000 kilometers a second is the maximum velocity that these galaxies move, which, while sounding very fast, is actually incredibly slow in terms of sort of being able to move them from one part to another in terms of this overall large-scale structure. And many people know now, for example, that Andromeda M31 is actually moving towards the Milky Way, and it's our closest nearby galaxy, and at some point we think the two will merge, but that merger will probably take about 5 billion years to happen. And so even though they're moving and they're slowing in the structure, it takes a long time for galaxies to move along these very, very large-scale filaments. Then at some point, if we think our current understanding of cosmology is correct, at some point, although tens of billions of years into the future, the expansion rate becomes so large that actually these structures start to be pulled apart. At least the filaments and the sort of larger scale structures will start to be stretched out by the cosmological expansion that's being accelerated by dark energy. I'm
sort of hoping it's going to be a big freeze, not a big rip.
Yeah, so again, the jury is still out in detail, but I think the evidence for a big rip is, it's not ruled out, but it's certainly not ruled in. It's, at the moment, you only need the cosmological constant. If dark energy is a cosmological constant, then we just have the big freeze out. But if it's slightly different from that and slightly sort of in one direction, then you do end up with the big rip, but not for a long time.
It's funny how that sort of thing is comforting for human psychology, even though we're talking, 20 billion years from now, 30, more than that.
That's right.
That's Professor Scott Kroom from the University of Sydney. And this is Space Time. I'm Stuart Gary. Scientists have discovered the most massive star ever known to have been destroyed by a supernova explosion. The findings, reported in the Astrophysical Journal and on the pre-press physics website archive.org, challenges current models of how massive stars die. The discovery may also be providing some fresh insights into the death of the very first stars in the universe. Our story starts with the detection of Supernova SN 2016 IET. It was discovered in November 2016 by the European Space Agency's Gaia satellite. Now, 3 years of intensive follow-up observations have shown some unexpected and difficult-to-explain characteristics. Supernova SN 2016 IET had an incredibly long duration and an unusually large energy output. It's also displayed unusual chemical fingerprints and an environment poor in metals for which there is simply no analogues in the existing astronomical literature. The study's lead author, Sebastian Gomez from Harvard University, says when he first realized how thoroughly unusual this supernova was, he felt sure his data must have been corrupted somehow. But after a while, Gomez and colleagues determined that this supernova was indeed an incredible mystery, located in a previously uncatalogued galaxy a billion light-years from Earth. The authors used a variety of telescopes around the planet and in space to show that SN 2016 IET is very different from the thousands of supernovas which have been observed by scientists for decades. It seems everything about this supernova looks different. Its change in brightness with time, its spectrum, that is, its chemical composition, the galaxy it's located in, and even where it's located within its galaxy. Astronomers often see supernovae that are unusual in one aspect or another, but otherwise they all follow a fairly normal pattern. But this supernova is so unique in every possible way. The observations and analysis suggest that SN 2016 IET probably began as an incredibly massive star around 200 times the mass of the Sun. And more amazingly, it somehow mysteriously formed in isolation, roughly 54,000 light-years from the center of its host dwarf galaxy. The star lost about 85% of its mass during its short life of only a few million years, all the way up to the time of its final explosion and demise. It was the collision of debris from the supernova with material shed during the final decade before the explosion which led to SN 2016 IET's unusual appearance, providing scientists with the first strong case for what's known as a pair instability supernova. Now, pair instability supernovae occur when pair production, that is, the production of free electrons and their antimatter counterpart positrons in a collision between atomic nuclei and energetic gamma rays, temporarily reduces the internal pressure supporting a supermassive star's core against gravitational collapse. This pressure drop leads to a partial collapse, which in turn causes greatly accelerated burning in a runaway thermonuclear supernova explosion. That results in the total destruction of the star, leaving no supernova remnant, such as a neutron star, in its wake. Pair instability supernovae can only occur in stars with a mass range from around 130 to 250 solar masses, and low to moderate metallicity, that is, a very low abundance of elements other than hydrogen and helium, the original elements produced in the Big Bang. Now that's a situation common to population 3 stars, the very first stars created in the universe. The idea of pair instability supernovae has been around for decades, but this is the first observational example with the right regime and composition. The authors say SN 2016 IET represents the way in which the most massive stars in the universe, including the very first stars, would have died. The team will be continuing to observe and study this supernova for many years to come, and they'll be looking for additional clues about exactly how it formed and how it's been evolving. Gomez says most supernovae will fade away and become invisible against the glare of their host galaxies within a few months. But because SN 2016 IET is so bright and so isolated, scientists will be able to continue observing its evolution for years to come. A truly fascinating example which proves how the universe isn't just stranger than we imagine, but stranger than we can imagine. You're listening to SpaceTime. Still to come, the mystery particles being ejected by the NearEarth asteroid Bennu, and New Zealand launches another Electron rocket into orbit. All that and more still to come on SpaceTime. Shortly after NASA's OSIRIS-REx spacecraft arrived at the asteroid Bennu, an unexpected discovery by the mission's science team revealed that this asteroid could be active, or at least consistently discharging particles into space. The ongoing examination of Bennu and its sample that will eventually be returned to Earth could potentially shed light on exactly why this intriguing phenomenon is occurring. The OSIRIS-REx team first observed the particle ejection event in images captured by the spacecraft's navigation cameras back in January, just a week after the spacecraft entered its first orbit around Bennu. At first glance, the particles appear to be stars behind the asteroid. But then on closer examination, the astronomy team realized the asteroid was actually ejecting material from its surface. After confirming that these particles didn't compromise the spacecraft's safety, scientists began dedicated observations in order to fully document the activity. OSIRIS-REx principal investigator Dante Loretta from the University of Arizona in Tucson says the particle ejections are among Bennu's many surprises, and it sparked the team's curiosity, spending several months investigating this mystery to try and better understand how Bennu and asteroids in general behave. The team observed 3 large-scale particle ejection events, the first on January the 6th, another one on January the 19th, and the third on February the 11th. They found the events originated from different locations on Bennu's surface. The first originated in the southern hemisphere, and the remaining 2 both occurred near the equator. The only thing they really had in common was that all 3 events took place on what would have been late afternoon on Bennu. The team found that after ejection from the asteroid surface, the particles either briefly orbited Bennu and fell back onto its surface, or they escaped from the asteroid completely and floated away in space. The authors also observed that the particles were travelling at speeds of up to 3 meters per second, and they ranged in size up to 10 centimeters wide. Approximately 200 particles were observed during the largest event. That's the one which took place on January the 6th. The science team looked at a wide variety of possible mechanisms that may have caused these ejection events, and they've now narrowed the list down to 3 possible causes: either meteoroid impacts, thermal stress fracturing, or released water vapour. Now, meteoroid impacts are common in the deep space neighbourhood of Bennu, and it's very possible that small fragments of space rock are hitting Bennu where OSIRIS-REx can't observe it, and shaking loose particles with the momentum of their impact, sending the debris flying in space. The authors also determined that thermal fracturing is another reasonable explanation. See, Bennu's surface temperatures would vary drastically over its 4.3-hour rotational period. Although it's extremely cold during Bennu's night hours, the asteroid's surface would warm significantly, reaching its maximum temperature in mid-afternoon, which is when all 3 particle ejection events occurred. As a result of this temperature change, rocks may have begun to crack and break down, and eventually particles could be ejected from the surface. This cycle is known as thermal stress fracturing. The third option, water release, could also explain the asteroid's activity. When Bennu's waterlogged clays are heated, the water could begin to release and create pressure. Now, it's possible that as pressure builds in cracks and pores in boulders where absorbed water is released, the surface could become agitated, causing particles to erupt. The team have reported these possibilities in an article in the journal Science. But the thing is, nature doesn't always allow for simple explanations. One of the study's authors, Steve Cresley from NASA's Jet Propulsion Laboratory in Pasadena, California, says it's very possible that more than just one of these mechanisms could be at play. For example, thermal fracturing could be chopping the surface material into smaller pieces, thereby making it easier for meteoroid impacts to launch pebbles into space. Now, if thermal fracturing, meteoroid impact, or both are in fact causing these ejection events, then this phenomenon is likely to be happening on small asteroids all over the place. That's because they all experience these sorts of mechanisms. However, if water release is the cause of these ejection events, then this phenomenon is very specific to only asteroids that contain water-bearing minerals, asteroids like Bennu. The material returned to Earth from Bennu will almost certainly increase science's understanding of asteroids and the ways they're both similar and different. Launched from the Cape Canaveral Air Force Station in Florida aboard an Atlas V rocket on September 8, 2016, the 2,110-kilogram OSIRIS-REx spacecraft arrived at Bennu in October 2018. The probe's spending 3 years orbiting the asteroid at altitudes as low as 5 kilometres, mapping Bennu's surface and geology and studying its evolution, composition, chemistry and mineralogy. One of the mission's key objectives will involve understanding non-gravitational influences, such as the Yarkovsky effect, in which sunlight hits the surface of an asteroid and that heat is then radiated back into space, providing a small amount of thrust as the asteroid rotates. And knowing Bennu's physical properties is crucial because scientists are trying to determine the likelihood of this mountain-sized rock slamming into the Earth. In July 2020, OSIRIS-REx will fly down and hover just above Bennu's surface, extending a robotic arm and collecting up to 2 kilograms of pristine asteroid regolith for a sample return to Earth. The spacecraft slated to leave Bennu in March 2021, with a sample return capsule being jettisoned for a parachute landing in Utah in September 2023. So, why is it so important to understand Bennu? Well, this asteroid's part of the Apollo group of asteroids. That means it's a NEO or near-Earth object. These are potentially deadly space rocks whose orbits intersect with and cross the orbit of Earth around the Sun. And Bennu's not exactly tiny. At 492 metres, Bennu hitting the Earth would be the equivalent of a 1,200 megaton thermonuclear explosion. Bennu is thought to be a Type B carbonaceous asteroid, generally similar to Type C carbon asteroids, but with surface spectra suggesting anhydrous silicates, hydrated clays, organic polymers, magnetite and sulfides. It currently has one of the highest known chances of hitting the Earth, with a 1 in 2,700 chance of impacting our planet sometime between 2175 and 2199. To make matters worse, its orbit is intrinsically dynamically unstable. Now, on average, an asteroid the size of Bennu can be expected to crash into the Earth roughly once every 130,000 years or so. Dynamical studies have predicted a series of 8 potential Earth impacts by Bennu between 2169 and 2199. Bennu will pass just 750,000 kilometres above the Earth on the 23rd of September 2060, and that close approach will affect the next close encounter on the 25th of September 2135. That's expected to be somewhere around 300,000 kilometres, but it could be as close as 100,000 kilometres. Now, there's no chance of an Earth impact in 2135, but depending how the asteroid's affected by that close encounter with Earth, future encounters with our planet start to get really interesting. The thing is, the asteroid could pass through a 55-kilometre wide gravitational keyhole, and that could create an impact scenario in a future encounter. On the 25th of September 2175, there's a 1 in 24,000 chance of an Earth impact. But it's more likely to miss the planet passing at a safe distance of roughly 15 million kilometres. The most threatening chance of an impact by Bennu with the Earth is on the 24th of September 2196, when there's a 1 in 11,000 chance of an Earth impact. Now, when you look at the big picture, the cumulative effect of all these potential chances of Earth impact indicate that Bennu's likelihood of hitting the Earth is roughly 1 in 2,700 sometime between 2175 and 2199. This report from NASA TV.
The Milky Way, home to billions of stars, rising and setting over billions of worlds, including our own. In this vast expanse, how did our sun, the Earth, and the planets come to be? In recent decades, our understanding of the solar system's evolution has greatly improved, but deep questions remain. To answer those questions, astronomers are preparing to visit someplace very small. Asteroid Bennu. A lump of rock and organic material, the early building blocks of the solar system, of Earth, of us. Bennu is a time capsule, and its journey takes us way, way back, 4.5 billion years. The raw ingredients of Bennu and our solar system originated in a stellar nursery, a vast cloud of hydrogen, helium, and dust. Our own sun doesn't yet exist. Nearby are hot stars like this one, quickly burning up its fuel and destroying itself in a colossal explosion called a supernova. The explosion destabilizes our cloud, causing it to collapse. In the geologic blink of an eye, 100,000 years, gravity and angular momentum flatten the cloud into a swirling disk. In the center, where molecules crash together tightest, a protostar revs up to incredible pressures and temperatures. Deep within the disk, clumps of dust not much larger than a grain of wheat are flash heated into droplets of molten rock, called chondrules. The source of this heat remains a mystery. Chondrules are destined to become the building blocks of the solar system. Coaxed by gravity and turbulence, the chondrules clump. They grow into the first asteroids, into mountains, into planets. The asteroids are rubble piles of rock, metal, ice, and organics. The parent body of Bennu, a protoplanet whose size we can only guess. Closer to the protostar, a planet begins to form. And then, dawn in the solar system. The protostar undergoes fusion and ignites, revealing our sun. But the solar system is far from finished. Jupiter most likely forms near its outer edge, but just 500 million years after the sun ignites, some believe that it slowly moves inward. Its massive gravity ripples the asteroid belt, disrupting countless asteroids and comets, flinging them toward the sun. They rain down on the inner planets, hammering and remelting large portions of their crust. Did these impacts also deliver organics and water, key ingredients for life? Back in the asteroid belt, Bennu's parent body is lucky. It survives this period of heavy bombardment. The solar system cools and calms. Jupiter and its many moons assume the orbits that we see today. Billions of years of quiet follow, more or less. Then 1 billion years ago, one theory suggests a collision shatters the protoplanet. Some of the debris loosely coalesces into a new, smaller body, Bennu. But Bennu will not stay in place. Dull, non-reflective, it slowly migrates toward the sun. Solar heating turns its warm side into a low-intensity thruster. Through millions of years, Bennu's orbit gradually tightens until it interacts with Saturn's gravity, altering its trajectory and hurling it into the inner solar system. Close encounters with Earth and Venus follow. Their gravitational tugs may have repeatedly stretched and reformed Bennu, turning it inside out and pulling off loose material. As a result, it has no satellites of its own, until now. Today, NASA is sending a spacecraft called OSIRIS-REx to explore Bennu and retrieve a sample. Why? Bennu has survived its long journey and settled into a near-Earth orbit, bringing its secrets within our reach. Now it is ready to teach us more about the solar system's history, its formation, its evolution, and our own place among the stars.
Now, while we're on the subject of near-Earth asteroids, which could pose a threat to our planet, and with 2019 not over yet, the year has already broken the record for the most amount of near-Earth asteroids discovered. In fact, during the past month, astronomers have discovered some 175 new near-Earth objects, and that brings the year's total to 2,144 NEOs since January the 1st. It also brings the total number of known near-Earth asteroids and comets to 21,429 asteroids and 108 comets. In fact, over the past month, 4 small meteors slammed into the Earth's atmosphere, and another 9 came within half the Earth-Moon distance in close flybys. And the near-Earth objects risk list, that is the list of the most dangerous near-Earth objects, has now increased to 982, with one new object, 2019 WW4, entering the top 10 list. 2019 WW4 is around 400 metres wide. That's not much smaller than Bennu. And based on what we know so far, it does have a very slight chance of hitting the Earth. Not much, but a slight chance in 2055. You're listening to SpaceTime. Still to come, New Zealand launches its 10th Electron rocket. China undertakes 2 rocket launches from the same launch complex within 6 hours. And later in the science report, global emissions of nitrous oxide, the third most important greenhouse gas, are accelerating. All that and more still to come on SpaceTime. Rocket Lab has successfully carried out its 10th Electron launch, carrying the Japanese Shooting Star satellite into orbit. The mission, named Running Out of Fingers, was launched from the company's Mahia Peninsula launch complex on the far eastern coast of New Zealand's North Island.
Rereading engines.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1.
Beginning pitch over.
Stage 1 propulsion is nominal. Enter check run 1.
There it goes. Rocket Lab's 10th Electron has now left the pad and is on its way to space. With over 1 million horsepower at its back, Running Out of Fingers will quickly reach the toughest point in its battle against physics, the moment known as maximum aerodynamic pressure, or Max 2. So let's check in on Electron's performance.
Enter check run 2.
Vehicle is supersonic. Approaching max Q. Cleared max Q. Guidance is nominal.
We've made it past Max Q, and Electron continues nominally. Soon the 9 Rutherford engines on Electron's first stage will shut down ahead of its separation from stage 2 and its descent back to Earth. It will be our first attempt at a guided atmospheric reentry of the booster, and we're hoping to be able to update you on how that goes after the mission. Once Stage 1 and Stage 2 have separated, the final vacuum-optimized Rutherford engine on Electron's second stage will come to life and propel Electron the rest of the way to orbit. Let's check back in on the operators in the lead up to stage separation and Stage 2 ignition.
Green burnout detect mode.
Stage 1 MECO.
Stage separation succeeded.
Stage ignition.
Recovery telemetry nominal.
Main engine cutoff is now confirmed, and Electron's first and second stages have successfully separated.
Guidance is nominal.
Soon the fairing will
Speed
separate
is
and jettison from
2.3
Electron's kick
kilometers per
stage.
second. Altitude 104 kilometers.
Fairing separation succeeded.
Stage 2 propulsion is nominal.
Looks like we've had a successful jettison of the fairing. With that out of the way, we're now 50 minutes away from the start of our scheduled payload deployment. Electron's second stage Rutherford engine continues to burn bright as it propels its payloads into orbit. Stage 1's first controlled re-entry into the Earth's atmosphere. The data we receive from this guided re-entry will aid in our future recovery plan.
HVB battery discharge is nominal.
The next milestone to check off is one that's unique to Rocket Lab and Electron. The Rutherford engines are powered by electric pumps. Electron is in fact the world's only orbital launch vehicle with this feature. These pumps are powered by batteries, and as you can imagine, it takes quite a bit of power to reach orbit. Initially, a pair of batteries serves as the power source, but once these are depleted, we swap power over to another fully charged battery and then jettison the depleted ones. We call this process the battery hot swap.
Guidance is nominal. 185 seconds remaining.
Electron's velocity is 14,000 kilometers per hour, and our altitude is 200 kilometers as we approach battery hot swap.
HVB battery discharge nominal, approaching hot swap in roughly 30 seconds. The APS has saved. Hot swap successful.
HV battery eject succeeded.
As you've just heard, we've had successful battery hot swap. Electron's second stage engine continues to burn 6 minutes and 45 seconds into the mission. We're currently 7 minutes, 15 seconds into flight, and with the mass of the depleted batteries out of the picture, Electron now has a much more efficient ride to orbit. All systems are nominal as we approach second engine cutoff in around 40 seconds. Our velocity is 21,000 kilometers per hour, and our altitude is 204 kilometers. Shortly we'll have cutoff of the vacuum-optimized Rutherford engine on Electron's second stage, followed by separation of the kick stage.
Terminal.
Let's check back in with mission control.
Entering stage 2 burnout detect mode.
Stage 2 shutdown.
Vehicle is in transfer orbit. Apogee is 385.97 kilometers. Perigee is 186.01 kilometers. Inclination 97.01 degrees.
And we have confirmation of kick stage separation. Electron's Running Out of Fingers mission is now orbital.
The primary payload, developed by Astrolife Experiences, was a small prototype for a spacecraft that will eventually fire artificial shooting stars into space, providing a spectacular meteor light show during the 2020 Tokyo Olympics opening ceremony in June. The mission also carried 6 Pocket Cube microsatellites built by Glasgow-based company Alba Orbital. These satellites provided a range of technology demonstrators and experimental scientific payloads, including one project measuring human-made electromagnetic pollution from space, another testing new thermal insulation material for use in space. A third satellite is so small it could fit in the palm of your hand. It's designed to test low-powered RF communication systems. Another satellite's designed to provide flight tracking and mobile weather radar applications, while the final 2 satellites will test intersatellite and satellite-to-ground communications technologies. The Electron rocket first stage used on this flight also tested new guidance and navigation hardware and sensors, including S-band telemetry and onboard flight computer systems designed to gather data during the first stage's atmospheric re-entry. The first stage was also equipped with a reaction control system to help it orient the booster during the descent. This equipment's all part of ongoing plans to make the Electron rocket reusable. This aerothermal decelerator package is designed to slow the jettison booster down as it re-enters Earth's atmosphere following main engine cutout and stage separation. As it descends, the Electron first stage would orient itself, then deploy guided parachutes. Rocket Lab plans to use helicopters equipped with grappling hooks to snag the parachutes and their attached rockets in mid-air, recovering them for refurbishment and eventual reuse on future flights. China has just carried out 2 space launches in less than 6 hours from the same facility. Both launches involve Kuaizhou 1A rockets taking off from the Taiyuan Space Launch Complex in northern China's Jiangxi province. The Kuaizhou 1A is a low-cost solid fuel rocket designed to carry payloads up to 300 kilograms into orbit. The first launch carried the Jingling 1 Gaofeng 02B optical remote sensing satellite. It'll now join Beijing's growing constellation of at least 14 other Gaofeng satellites now in orbit. The second launch carried 6 satellites into space. These included the Head 2A and 2B, which will carry out land surface monitoring, collecting information on global shipping and aircraft movements. Also in the manifest were the SpaceTime 16 and 17 medium-resolution nanosatellites, which will undertake remote sensing operations, and the Tianqi 4A and 4B satellites, which will provide global Internet of Things data transmission services. And time now to take a brief look at some of the other stories making news in science this week with the Science Report. A new study warns that global emissions of nitrous oxide, the third most important greenhouse gas, have increased for many decades, but that rate of increase has been steadily accelerating since 2009, above what previous estimates had been suggesting. Nitrous oxide comes from nitrogen-based fertilizers. It's a very potent greenhouse gas. In fact, in climate change terms, just 1 ton of nitrous oxide is equivalent to 298 tons of carbon dioxide. A report of the journal Nature Climate Change found that China, India and Brazil make the largest contributions to the nitrous oxide global increase. Interestingly, lots of other countries have shown that it is possible to increase agricultural yields without increasing nitrous oxide emissions. New research indicates that social media is leading young teenagers down a worrying path towards developing body image issues and eating disorder behaviour. The study by scientists with Flinders University and the University of Western Australia found that this was happening even though kids are smartphone and cyber savvy. The findings, reported in the International Journal of Eating Disorders, is based on a study of 996 middle school students aged 13 and 14 from years 7 and 8. The authors found platforms with a strong focus on image posting and viewing, such as Instagram and Snapchat, are the most used and the most risky. The recent CRISPR baby scandal, where rogue scientists in China edited the genomes of twins, may have resurrected talk of designer babies, but new research from Israel suggests that even if people wanted to go down this road, the science is still a long way off understanding how modifying genomes could allow people to select certain traits. A report in the journal Cell claims most personality or physical traits are determined by multiple genes, and science just doesn't know enough about how they all fit together to begin to even understand the cascading effects manipulation might have. Scientists ran a computer simulation of what might happen if they modified hypothetical embryos to be taller and smarter. But they found the expected advantages to these theoretical offspring were relatively small and couldn't be guaranteed. IBM has uncovered a new strain of malicious wiper malware being deployed by Iran's state-sponsored hackers. The attack was led by Tehran's APT-34 hackers group. They hit the headlines earlier this year with that phishing attack targeting people using the LinkedIn social media group. But APT-34 didn't act alone. In this latest cyber attack, they were supported by another Islamic Republic-based hacking group called APT-33. They're best known for malicious malware targeting Microsoft Outlook and another virus called Shamoon, which misuses LDOS raw disk to target computer files and disks. This new Iranian cyber attack, which has been codenamed Zero Clear, is based on Shamoon and overwrites the master boot record and disk partitions on Windows-based computers. This latest attack shows that Tehran's hacking groups are now demonstrating an increasingly sophisticated set of cyber weapons with which to target the West. Are you devastated every time you ask your dog to do something and they just sit there looking at you, only to see them instantly obey when your partner requests the same thing? Well, the bad news is they're doing it deliberately because they can definitely understand what you're saying. New research reported in the journal Biology Letters found that dogs can distinguish familiar words, even when those words are being spoken by unfamiliar people. The research also found that dogs can hear a string of unfamiliar words and pick out whether they're being said by the same person. What I guess this all shows is that sometimes even dogs can be real jerks. And that's the show for now. You can subscribe and download SpaceTime as a free twice-weekly podcast through Apple Podcasts, Stitcher, Bytes.com, Pocket Casts, SoundCloud, YouTube, Audio Boom, from SpaceTimeWithStuartGary.com, or from your favourite podcast download provider. If you want more SpaceTime, check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as loads of images, news stories, videos, and things on the web that I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word and in lowercase, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram. On Facebook, just go to www.facebook.com/SpaceTimeWithStuartGary, and you can also find us on the SpaceTime with Stuart Gary YouTube channel. SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.